Okay.
Great, welcome to the second episode of Statistically Speaking. I hope that everyone received an email that had the URL for YouTube for the last episode. Also, that email should have had a URL to a shared drive, a shared folder of my Google Drive. And if you look in that same folder, you should find some files for today's session as well. I have that URL open, I believe. It should point you to a directory. Oh, I've got to close that slideshow first. That should guide you to a shared directory that has these files in it. So today I'll be presenting these slides. They're available here in PDF format. And we have two input files that we're working with for the demonstration today. One an Excel file, one is just a script of R. So I hope that you have access to that. If you don't, let me know and we'll get you the URL for that again. It's kind of long to type, so it might be easier to find in your email. Okay.
Yeah, maybe it's best for people to just download it right away. We have breaking internet.
The network is intermittent, yes. Yeah. I tried to upload my video from last week's lecture from my home computer over my DSL line, and it was egregiously bad. I waited until I got into the office the next day to send it as a result, yeah. Well, we've spent a little bit of time talking about different distributions and logarithms as well for the kinds of metrics that we work with frequently in biotech. This week, we're going to talk about spread. So I want to put you in a situation where this had great relevance. I was sitting in my office one day interviewing a student who wanted to become, a former student who was hoping to become a programmer with my team at Vanderbilt University. And I thought, I had a wonderful glowing conversation with the person, the classes that she had taken and so on, all sounded really great. But I had seen that she had a full year of statistics training as an undergrad, and I wanted to make sure that some of it had sunk in for her. So I asked her, in the context of a normal distribution, what does standard deviation mean? What does standard deviation mean? And she got this panic-stricken look on her face and fell completely apart. Had no idea how to answer that question after a year in statistics courses. So I'm hopeful that today we can get you to a place where you can answer that question firmly. Now, I'll say that the weakest answer that would have scored points in that interview with me was if she had said fat or skinny, right? If you've got a narrow standard deviation, you have a narrow distribution. If you have a very large standard deviation, you have a very wide distribution. So that would have been a starting place for us to talk about variation. But instead, the term just didn't register anything at all. So I hope that today you're going to get a strong sense of why knowing standard deviation is very valuable, and also what you can do when you don't have a normal distribution to work with. We'll also talk about some distortions that can appear in our data that cause them to look not like something other than like normal distributions. So I already mentioned this. We're going to be talking about variance, which is one metric we use for computing this, and standard deviation. These are most popular in the context of normal distributions. And we're going to talk about spread in general, what one standard deviation or two standard deviations out means. And then we'll talk about spread in the context of non-normal distributions. And we're going to talk about a couple different tests that we can use for normality, one being the QQ plot, and one being a Shapiro test. Okay, so when I first made this title, it read the hat, the cat, and the delta. But I realized that I was confusing the hat, which is sort of like a caret over a letter, for the bar. So I'm going to try to keep this straight in my mind. We have a random variable x. You see a lot of statistics conversations that start that way. And in this case, we're talking about a whole vector of numbers that's going to be associated with the variable x. And it has n members in it. We talked briefly about sample size. Frequently, n is the number of samples that you have in play. Okay, So now we want to compute its average value. Its average value. In this case, we are talking about a sample mean and a sample variance. So one of the most straightforward things we can do is figure out a central reference point to ask how much deviation we've got from each member. So for that, we have to compute a mean to work from. Mean is one of these concepts that just shows up all over the place, especially in connection with a normal distribution. Now, is it required that your data be normal in order to compute a mean value from them? Right, it could be any distribution. You can compute a mean from anything. What that mean will represent will differ, though, depending on whether you've got a normal distribution or not. So here we have x bar equals the sum of all the x values divided by n. So when we have these operators that sometimes freak people out, and they usually feel like they're jumping into hot water when they see this sigma value. So I just want to comfort everyone that this isn't so very bad. When we have a sigma in our expressions, it just means we're going to add them all up. So we want to add together all the members of x, and we want to divide by the number of those items. Lots of people have computed means, I assume, so this should not be terribly shocking, but here we're writing it a little bit more formally. We're also going to give x bar a particular meaning in this case. X bar is the mean value for x, the average. Okay. Now we can compute the sample variance with reference to x bar for this mean value. So we're now just going to assert that this mean value is the one around which all the other values can be assessed. We want to see them, see how much spread there is with reference to this central value. It could be that all of the values of x are perfectly identical. What will the variance be then? 0, right? Because this x bar will be identical to x sub I. So we're throwing a whole bunch of math terms out here, and I want to make sure everyone follows every piece of this. We've said that there are n different values in x. So what's this x sub I business? Where's the I coming from? I've used a bit of a shortcut. So normally, if we write our sigma notation properly, we have a little value below here and a little value above here. Because the sigma represents an operation on a whole sequence of numbers. So technically, when we use a sigma, we really should write I equals 1 up to n, which is to say we're going to start. I'm going to close this door for just a moment. No need to follow me over here. It's okay. It's a very exciting place to work. Lots of people like discussing things in their outside their offices here. Okay. Oh, there we go. Blessed silence. So, with our sigma operator, we are assuming that we're going to start I at the first item in x, and we're going to run it up to n, the total number of items in there. So this is a bit of shorthand. It just says, we're assuming essentially that I is going to be all the different members within x. So for each member of x, we're going to subtract off the mean, and then we're going to square that value before we add it all up. Okay? Now, that's already a bit confusing, and we'll talk about that in just a moment. And we also have this n minus 1 business down below. So there are two questions that immediately pop out to me when I look at this expression. I asked first, why would we square the differences versus the mean? And why would we divide that by 1 less than the number of items that we're adding together? It's a little puzzling, isn't it? Welcome. Glad you could make it. Okay, so I'm going to try to answer both of those questions. The first is that when we are evaluating differences versus a mean, squaring that difference puts a greater penalty on being a little bit further away. Because imagine a difference of 4 versus the mean versus a difference of 5 from the mean, right? A distance of 4 is going to get a variance penalty of 16, but a variance of 5, just 25% further, gets a penalty of 25. 25 versus 16 is a pretty big, hefty weight to throw at things. So by squaring this distance, this delta value, that's where this comes from, we're going to add a greater penalty on being, for every step you are further from the mean. The squaring is a very common measure that we see, and as we look at something like correlation next week, we're going to see that this squaring actually has a pretty important effect. Okay, so that covers this first part. We have a delta from the mean value. We're squaring it, and we're going to divide that by n minus 1 terms. Now that's going to bring in another concept that shows up frequently in statistics called degrees of freedom. So why would we do n minus 1? I'm going to explain that this is because we're already using this information to compute our center point. So in effect, the center point stands in as another item on our roster, and we can't compare a center to itself. So we are subtracting off this one value to reflect that has been included. All right, so I've also thrown in yet another name for variance here, the s squared, or sigma, lowercase sigma squared value. This is a common way for us to name variance s squared. All right, now what's my title? The bar, the cat, and the delta. So the bar is over here. We had our x bar, the most typical value, the average value of x. And we have the delta over here, which represents the difference of an individual point from the mean value. But where's the cat? Bit of clip art. I like cats. Okay, but why do I have it pointing up here?
Because the sign is called mu.
Ah, very good. Yes, this is a Greek letter, sometimes pronounced mu, sometimes pronounced mu. But I could not allow a mu to pass without a friendly cat to produce the sound. So mu, delta, and the bar. These are all three things that we should have very firmly in our mind. The bar being the average value for this thing, the mu being the mean, or the x bar being the mean. They're identical in that way. And of course, our delta being how far an individual point is from the most typical value. Great. Now I've included some URLs down here. These are fairly basic tutorial sites that may help you if you run into some problems understanding these things. Now, as I mentioned, this is producing a sample mean rather than a population mean. The two differ very, very little, mostly by this minus 1 value here. Okay, so now before we were talking about s squared, a variance value. Here we're doing lowercase sigma, which is this weird little symbol. That is our way of naming standard deviation. Okay? So standard deviation is the square root of variance. We just computed variance in the last slide. Take the square root of that. You can instead call it a standard deviation for a normal distribution. Now, over at the right, we have our friend, the standard deviation. Here we're just showing the probability of each value for a standard deviation with mean 0 value. The x bar is 0, and then the SD, the standard deviation value, is 1. So I've drawn in some bars on top of this, and I want to note that these green bars indicate standard deviation 1, or standard deviation of minus 1 for that matter. It's symmetric. So when we talk about being within one standard deviation of the mean on a distribution, it means that we're accounting for about 68% of all of our data. So if you have just random samples drawn from something that's normally distributed, you expect, if it's normally distributed, 68% of the values will fall within the 1 to minus 1 bracket. If you extend out to 2 standard deviations, you've reached about 95%. Okay? Now, do you gain as much in going from standard deviation 1 to standard deviation 2 as you did going from 0 to 1? Not quite as much, right? So 95% minus 68% is 27? About 27% more. So we started with 68% of the data accounted for by 1 standard deviation. We added another 27% to get us to 95% within 2 standard deviations. And look what happens when you step out to 3 standard deviations away. 99.7%. So if you see data that fall more than 3 standard deviations away from a mean, you can probably say this is something of an outlier. You could be right on the tail, right? I mean, you could be sitting right here, and that's a more likely outcome than if you're very far away. Has anyone heard of a certification called 6 Sigma? 6 Sigma. 6 Sigma is shorthand for 6 times the standard deviation. They want to produce business processes that are so reliable that they are way outside, that the typical behavior of processes is completely predictable. So their 6 Sigma is intended to trim off all of these things outside the distribution of behavior. Okay, so here we have our plot. Now I've included the R code for showing this on top of this. So we started by giving us a sequence of values from -4 to 4 in 1% increments. We've created a density plot to show what the probability of achieving a value this far from the center would be. We've created a plot of line type, and because my eyes are bad, I did line width equals 3 to make the line a little thicker. We gave us a Y label of probability and a main label. I didn't label the x-axis, I labeled the top of the graph. Mean equals 0, standard deviation of 1, to remind us what the parameters were for this. And all of these are a new command that I didn't include last week, and I wanted to make sure you guys knew about it. The AB line option is one of the easiest ways to superimpose a line on an R graph. So in this case, I've created a horizontal line running across the bottom in black. This represents, is put in at h equals 0, so the y value is set to 0 for this line, and it just shoots right across. Here I've thrown in my green lines by specifying that they appear at 2 different x values, -1 and 1. They are colored green, and again they're thick. The lines in blue that appear at ±2 are in green, are in blue, and then ±3 I've labeled in violet. So you can see that's a pretty straightforward way to do it. The only thing you need to do to change from a vertical to a horizontal line is this h or v parameter. You can also use lines that have a formula to them, so they have a proper slope. That's called very slightly differently, but it's still the AB line option. And folks can also see that changing the color of those items is as simple as changing the parameter color that you pass to it. Also very helpful. Okay. So, do I have a question? No question, okay. So, for centrality, there are 3 terms that I think everybody should have in mind all the time when you think about a distribution. Mean is the average value among all the different points that you've got. We just looked at how to compute that, the sigma over n. Even the outliers contribute to the placement. That might seem like a throwaway phrase, but it's not. Even outliers contribute to the location of the mean. So if your data are not properly Gaussian, if instead you have a whole bunch of values that are way out on the extreme ends, those are going to have a disproportionate impact on the placement of the mean. You know, if you have the values 4, 6, 5, 7, 4, 6, 5, blah, 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 plus 1,000, a value of 1,000, the 1,000 is going to push that mean way up high, especially when you have relatively few values down in the 4 through 7 range, say. Okay, so outliers contribute to where the mean shows up when you produce a sample mean. Median values. A median value is completely different. It does not care about magnitude at all. Instead, we sort all of our data points from the lowest to the highest, and then we ask which one falls in the middle of that list. Okay, so a quick question for you. What happens if you compute the median of 6 items? Median of 6 items.
You add the 2 in the middle?
Right, so when you have 6 items, there is no middle value in the list. Both the middle 2 have the claim to being in the middle. So what you do is take the average of those middle 2. Okay, so the median doesn't care if the maximum value you had in that last distribution was 1,000 or not. It's a high value, it's to the right of the median, and the values that remain are going to be used to figure out where the median is. So if you have 7 items, the 4th item is the one that gets picked as the median, whatever its value is, goes. All right, so think of this as a rank-based assessment of centrality, and the first one is this magnitude-shaped one. All right, and finally, mode. Mode is the most common value. So in a mean, in a normal distribution, a mean is most frequently the mode as well. So the most frequent value is going to be of more importance if we're talking about about data that have a step to them, right? So if you have, if you're dealing only with rounded numbers, 4, 5, 7, 8, 4, 4, 6, 2, then the mode is going to become more meaningful. Otherwise, you kind of have to do something like, where is the probability distribution highest? And that'll come up in just a minute. So let's start with this concept of bimodal distributions. Bimodal. That just comes from the phrase meaning two modes, right? So if we look at this, we see that there's a hump centered on -2 and a hump centered on +2. This is not a normal distribution. In fact, it's the sum of two normal distributions superimposed upon each other. These show up a lot of the time. I work in proteomics, for example. One of the things that we deal with is the problem that some of the spectra we work with are identified successfully, and some of the spectra that we've tried to identify, we identified unsuccessfully. So if you glom together all of these results, just sort everything by score, what you see is that you've got this big hump that represents spectra that were identified unsuccessfully, and a second hump at a higher score that represents the spectra we identified successfully. And if the number of spectra you identified successfully is quite small, maybe 10%, it doesn't really form a second mode. It just sort of makes it look like it's got this long tail at the high scores, right? So frequently, in biological data, you can expect to find mixtures where multiple distributions have contributed to the score distribution overall. Now, how did I do that? In this case, I used the compose operator again, or function, to add together two different distributions. I said I wanted 1,000 values drawn from a normal distribution with a mean of -2, and I said I wanted 500 drawn from a distribution that has a mean of 2. So we can see that when we add all of those together, this second part creates this hump to the right, and the first part creates a hump to the left. And we don't have a baseline separation between them. These aren't resolved peaks. Instead, we see that both distributions are contributing to the values that we see at 0. So this is additive. If we were to draw this separately, we would see that those two distributions are both contributing members to that middle space. All right. The other thing that I want to note is that I'm not plotting I'm not showing a histogram here. Instead, I'm using something called a density plot. And density plot is really handy when you have a histogram, but you need to show greater granularity about it. So a density plot shows essentially how many values are near this value. So this value at 4 is not an exact value. It's summing across everything that's a little bit below 4 and a little bit above. Sorry, a little bit below 4 and a little bit above 4 as well. So density plots are useful when you want to smooth out those histograms and show things at finer granularity. Okay, and again, there's a link provided in the slide bottom there. All right, the next concept that I would bring you to is called skew. Skew. There are other things we can talk about as well, like kurtosis, etc., but frankly, I find them kind of confusing. So we're going to just start with skew as kind of a general concept. Now, remember I said that we wanted to think about 3 different kinds of central values. Means, which everyone thinks about, median, which is the center of the sorted list, and mode, the most common value. And the shorthand for mode is to look for the spot in the distributional plot that is highest. So the most frequent value is going to be the highest point in these curves. We see that the mode is always labeling the top of that curve. So what happens when we have a bunch of really low values thrown in with a bunch of values that are more typical for this distribution? We see that we have a negatively skewed distribution. And because the mean tends to go chasing after the most extreme values, we see that this preponderance of very low values has chased the mean off to the left of the median and left of the mode. Remember that the median is also going to push towards those extreme values, but only by changing which item in the list gets picked as the most typical value. Similarly, you could have a whole bunch of high values that have been thrown in on top of a standard normal distribution. And we can see that those high values, again, force the mean, push the mean the most, push the median a little bit less, but the mode is always the king of the mountain. The mode is always going to stay up at the top. Okay, so skew is one of those things that we need to recognize in our data if we're trying to use statistics that expect a normal distribution. That's really going to come into play once we start talking about t-testing and u-testing in 3 weeks, I believe. So for now, just keep in mind that needs to be considered. All right. Now sometimes our data aren't normal at all. Sometimes their distribution is quite a lot harder to deal with than that. So in this case, I want you to think about percentile means of evaluation. So the most straightforward thing that we can ask about the data is the range. What is the maximum value that we saw? What is the minimum value that we saw? Nothing is out beyond that, right? So we can compute the range by just subtracting the lowest value we saw from the highest. All fine. And oddly enough, we don't often see those data represented. One of the reasons that we sort of dislike range as a metric for distributions is that it's really hyper-responsive to extreme values. The very lowest value that you see is going to be forced as the minimum. The very highest value that you see is going to be dealt with as the maximum. Now, frequently, we're working with biotechnologies that don't give us complete data back. We may have missing values. For example, a batch of the Luminex assays produced foul results, and so we end up with not applicables in those locations. Sometimes we want to try to impute what those values should be. Or you might get a value back from the machine that says, this is a value higher than I can quantify, or this is a value lower than I can quantify. One of the typical ways we deal with this is to replace those values with the lowest value we saw overall, or the highest value that we saw overall. So in effect, the range of your observed values for which you did have a successful measurement becomes the minimum and maximum at which you impute values that were too high or too low. So range shows up a lot, and people don't think about it, but it's still there. Okay, next, quantiles. My first exposure to quantiles came when I was in grade school, in primary school. We would do things like the Iowa test of basic skills, and of course they didn't count towards your grade. Heavens no, not towards your grade. But your teachers seemed to care an awful lot about whether you did well or poorly on these things, right? So the Iowa test of basic skills for elementary school students was designed to see how the students were performing against national norms. Students in every school, every state, every school in the country were taking these tests, and so they would use this to say, are the students at this school average, above average, below average, or whatever? And the metric that they would use to report results was a quantile, or a percentile. So that percentile would be 90% if your scores exceeded 90% of all of those seen in a subject. Or your scores could be 30 or 40% to reflect that you were better than only 30% or 40% of the students that were taking the test. So those percentiles don't give you an absolute evaluation of your performance. They are a relative assessment versus the broader distribution of all students. Okay, so you can apply that to data and biotechnology just the same as you could with students. So you can say, if you have 86th percentile, this value is higher than 86% of all the values that I saw. That is a non-parametric, that's a term of art for statistics. It is a non-parametric way to describe this data point in relation to the other. Does it matter whether you have a uniform distribution or a normal distribution? Do you have the expectation that one or the other distribution is in play if you are presenting it as a percentile? No. It's distribution free. We don't care if you've got skew, if you've got a bias or whatever. We just care where this value stands in respect to the rest of the distribution. Great. Okay, so that's quantile. Now quartiles are a special case of this. The quartiles are a set of 5 values that reflect quarters of the data. We have our minimum and maximum. The range comes into play. So those tell us the bottom and the top of our quartiles. We also have the median, which we said fell halfway through the list. So if it fell halfway through the list, what quantile is it?
50%.
50, yeah. 100% of the data, so if you fell exactly in the middle of the list, you're above 50%. So yes, the 50th percentile has the special name of the median. All right, so we have those 3 points, and then alongside that we have the 25th percentile and the 75th percentile. So to think of it this, in one way, we're cutting our data into quarters, whether it's normal or uniform or Poisson, we don't really care. And we're separating the first 25% of our values from the second 25% of our values, the third 25%, and the fourth 25%. If you've got 4 zones, you have 5 boundaries. So that's why I say we have 5 quantiles, 4 areas. Okay, so there's a special name that we use for describing where the middle 50% of our data lie. They fall in the interquartile range. And sometimes you'll see software nicknaming that the IQR. The IQR. So the interquartile range is a non-parametric way to say where are the middle 50% of your data found. It's, again, non-parametric. You can do that with uniform distributions, exponential distributions, Poisson, normal, whatever you like. Okay. So that brings us to the QQ plot. Sometimes we want a graphical means to tell us how our data are distributed. This is a difficult place to be because there are frequently statistical tests we want to use, most typically the t-test or the ANOVA test, and we will talk about those later on, that expect our data to be normally distributed. But it might be that the data you've collected are not normally distributed. So being able to detect that your data are not from a normal distribution becomes very useful to you. And yet, one of the things that we're going to talk about as we walk through the tutorial after this is that our ability to detect whether or not our data are normally distributed requires an awful lot of data points to run successfully. So, how can we do this? One of the easiest ways to do it is to use a QQ plot. So in this case, we have run a QQ plot using the QQ norm function. We'll use it in the tutorial in just a moment, to plot out a randomly sampled set of values across a normal distribution. And what we see is that when we compare the sample quartiles to our theoretical quartiles, we get what is more or less a straight line falling on this, a line with a slope of 1. All right? That is valuable to us because falling on the slope of 1 in a QQ plot makes us feel more comfortable that our data truly are normally distributed. Okay. Now, I'm going to break out some more terms that we need to be thinking about. The second part of the slide is a little less commonly known, and I had to teach myself some aspects of this just to get it ran through my head. So I hope that you find this useful. There is this, if you simply look at a QQ norm plot, a QQ plot for a normal distribution, that might look pretty straight to you, but it doesn't deliver a number that says how straight is it. Right? So this is visual evidence that we have a normal distribution, but we kind of like to put a number on it. So Shapiro-Wilk is a test that we can use to evaluate whether or not data truly do come from a normal distribution. But it introduces a term that's going to show up in spades once we get to difference testing. So I really wanted to break this out. This is the null hypothesis. The null hypothesis. So H sub 0 is a bit of shorthand that we use to stand in for null hypothesis. So people always get null hypotheses confused when they're dealing with tests, and so I felt like it was really important to bring this one up right here and now. A null hypothesis is the only hypothesis that's really getting tested in the context of a statistical test. And in our case, our null hypothesis says the data do come from a normal distribution. So if I am able to disprove the null hypothesis, it doesn't mean that I've proven that my data come from a uniform distribution or from a Poisson distribution. It means that I can reject the hypothesis that they do come from a normal distribution. Okay? So the null hypothesis is the boring one. It's basically saying how likely are these data under boring assumptions. Okay. So if we get a very low p-value that results from a Shapiro-Wilk test, it means we reject the hypothesis that our data truly are normal. All right, so this is one of the things that we can use to evaluate before we run to ANOVA or t-test, that those tests are appropriate. Okay, I believe, oh no, I had some closing thoughts. All right, so let us start with this. So characterizing spread is very important. Our ability to find differences downstream depends on our ability to limit spread. This is one of those things that I'm going to be pounding on again once we get to difference testing. You want to say that items of type A are different from items of type B. So one of the things that you should be thinking about is the mean difference between those. If the distribution for A is far from the distribution for B, that's good for finding differences. But you also have to think about the spread in A and the spread in B. Because if you have very wide distributions for A and B, your ability to say that A and B are different goes away. So it's not just how far the differences are, it's how much spread you have in each of those two pools. Okay, next up. Just because data have a single hump, are unimodal, have only one high spot, does not make them normal. We have expectations about distribution in regard to variance and standard deviation that also must be met before we can say that the data are normal. Hi there.
Sorry.
Welcome. It's okay. Hey, it's a new class. We're all getting used to being here at 11 at school. All right, so being able to describe data in a non-parametric way is very valuable. Downstream, we're all going to have to deal at some point with experimental data that simply don't behave very nicely, that look a little squirrely. And being able to describe them in non-parametric ways means that we may be able to recognize tests that are appropriate for making sense of them. So we're going to get to that stuff downstream. But for now, I hope that these slides help introduce this concept of spread and get that drilled in. Now, we're not even close to an hour so far. I can feel that in my bones. Did I talk 20 minutes or 35 or what?
21.
What's that?
20 minutes left.
20 minutes left. I talked 40 minutes on that.
Yes.
Holy cow! What's wrong with me? Okay, now we have a question.
The slide just before this one.
Sure, yeah. This one?
When you say with the low key value, then you can reject the hypothesis, and that's always been a bone of contention for me. How do you then say the p-value is low enough for you to say I'm rejecting?
This is a great question. This is an excellent question. Actually, the whole field of science is grappling with this right now because a lot of people are producing a lot of p-values, and they're still using this 0.05 threshold laid down in early 20th century as the threshold. It's dangerous to us, right? So, all right. This is an example of a test that has only one hypothesis in play. You could imagine that you could make a more specific test if you were trying to decide whether your data were more likely under a uniform distribution or under a normal distribution, right? So you could ask, what is the probability that I would see this distribution of values under a uniform versus a normal, and that would give you a better ability to detect that. That's what we call that is a test of two hypotheses. The most frequent way for us to express that is to give the probability of one under one model versus the probability under the other model. Okay, so that's two hypotheses, each producing a p-value that we can compare in a log odds ratio. This is more generic than that. This is simply saying, do these data fit under this one hypothesis, that they're a normal distribution? So we have to have some way that we decide that this is or is not enough evidence to reject that hypothesis. So if we produce a value that is less than 0.05, by convention 1 in 20, we say it's significant. But the reality is that there are lots of ways you can foul that up. We will talk about multiple testing correction at a later stage because it's a really, really important topic. But for now, we're going to stick with the convention that 0.05 or less is a significant deviation from this. But yes, there are a lot of people saying that scientists should now use 0.005 as their value for significance. And yet I find a lot of people screaming, actually, when I say, this value that you're claiming is significant in your slide is not significant once you consider the fact you did 35 tests to get here. I get a lot of flack for that, actually, a lot of flack for that. One of the best things statistics can do for people is to protect them from their desire for a successful experiment. That's a harsh thing to accept. When we publish data, when we publish experimental findings, the person who's writing that article is the person who is most biased about that result. You're not doing experiments hoping to get a bunch of very high p-values. You know, you're doing experiments to provide the experimental data that points us in the direction that our advisor told us we had to go, frankly, in a lot of cases, right? Your advisor wants to see a significant p-value as well. So if both the person writing the article and the person who provides the funding for that article are biased in favor of a statistical test that produces a significant p-value, that's a dangerous situation. Science is filled with papers with erroneous false positives today as a result. And one of the things I hope to teach you to do is to protect yourself against your own biases. I want you and you and you to be the harshest critics of your work, to do the experiment that proves against a skeptical you that this idea is actually right. That's a hard discipline to teach yourself. You should always prepare your research for publication in a way that suggests that your worst arch enemy is going to review this manuscript. Your worst arch enemy is going to look at this. Maybe it's somebody who hasn't managed to bury the hatchet with your advisor for 20 years. For 20 years, they've been publishing articles on opposite sides of the same issue. Imagine that person is reading your article and is looking for every opportunity to poke a spear into it, right? So, if you are very critical of your work and can write defensively and use statistical models that are appropriate, not that give you significant p-values, you will protect yourself from a lot of grief downstream. You always want people to be able to trust what you say in your research papers. That's a hard thing. It's a hard discipline. Okay, so let us do some work with R, because I've written up this little guide to work us through that. There are 2 lessons I want everybody to get from today. The 2 lessons are, how can I get my data into R? It's sitting in an Excel spreadsheet, I want to get it into R. This is one of the key things that everybody's got to do at some point. So getting your data out of Excel and into R is one of the things, the exercises we're going to do. And one of the other things we're going to show is that you can define your own functions in R. You can create your own functions. So we're going to work through this with these 2. Okay, so you should have this text file dated 8/31 that's present in the Google Drive. Does everyone have that? If not, and you can type, if you can type very, very quickly, but this is all sitting in the shared drive for this folder. That shared drive is going to have the same URL for every week of this course. So you should always be able to find stuff there, and I'm dumping things in there before the class. So if you are having difficulty finding it, hi there, come on in. All right. This is the statistics discussion for IMBM. Okay. So I can get you the URL for this again if you like, but it's easier to just dig it out of your email, I think, because typing them out longhand is difficult. All right. So I started by giving you the code that I use to draw the standard deviation figure with all the AB line business in it. I'm not going to operate on that because I realize we're already sitting at 48 past the hour. But I wanted to give us some data that we've read from a text file. So let us start with the fact that I have an Excel sheet. The Excel sheet is sitting in that directory, so you should be able to get it pretty easily. Now I've grabbed numbers from the 2011 census from Stats South Africa. I have each province, and I have the population for each. So this is a pretty simple spreadsheet. So I want you to note that the first row constitutes a header that gives a name for what each of these data fields represents. Now, I need to, it is possible to read an Excel spreadsheet directly in R. We're not going to do that though. We're going to use a much simpler function for reading comma-separated values files. Okay? This is called a delimited file. We're going to write on each line of that file a text string followed by a comma followed by a number. So in this I simply say save as, and then I need to give it a new file type. You can see I've got CSV UTF-8 blah 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 blah. The important thing is that it is a CSV file. Oh, there's also comma delimited down here. They're going to have the same result. Comma is not the only way to delimit, to set one field apart from another. Another kind of file that we frequently see is called a tab-separated values file, a TSV. Now, for family reasons, I might use the TSV format, but CSV is very common as well. You see both. My last name is Tab. That's not a very good joke. I appreciate that. Okay, so I'm going to say I want a CSV file, and I'm going to save it. Yes, it exists. I know. I'm not worried about that. Okay, so what happened? When I look in this directory, I see that I now have a CSV file. In fact, Excel wants to be the software that opens it, but I'm going to cheat a little bit. I'm going to open my text editor, and I'm going to drag that file over. So here's CSV, blah, 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 blah. Okay. So we see that that header line shows up as province, comma, population 2011. Those were the two column headers that I had. In each row I have the province, comma, and then the value associated with it. Not a very complex text file. You're probably working with things that have 50 samples, each measured 500 ways. So you can do this with those large spreadsheets. You can do it with a small spreadsheet. Something you need to be really cautious about when you're doing comma-separated files is to be absolutely sure that none of your cells contain commas. If they do, all sorts of squirrely things can happen. So be cognizant of that. If you're using comma separation or tab separation, don't have extra tabs or extra commas in your spreadsheets. Okay, so now I have a file here. I'm going to close it here. Oh, I just closed the whole thing. That's terrible. All right, I'm going to open this again. I'm going to reopen the script, which is right here. Shoot. Options, set default font, map to consoles, back to 18 point. Okay, great. There we go. So we're going to go down to this code. How do the provinces differ in population? We're going to start by reading this file in R. Now I have to do something very, very important before I attempt this. I've opened the software here. I'm going to use the list files command. This is its current directory content. It does not see this populations file. That's because R is in the wrong directory. So instead, I'm going to pop up here to the top of the menu and say change directory. Now for me, I've got this really crazy long path name that gets me to where those files are held. So we're going to go to my own cloud directory, to documents, to Sun archives, to courses, to statistically speaking, right there. All right, open. Okay, so now let's do list files again. Ah, great. I can see the files. This is good. So to return to my script, I'm going to start by using the read CSV function and store the output in the field in a direct variable named provinces. I copy that, paste that here. So I can type provinces by itself, and we see that these values have been read in successfully. And look, it did a little bit of magic for us. Well, that's a little squirrely. I'm not sure where that letter is coming from. But it sees that it has assumed that I had a header row on this file. And so the first row became province and populations as labels for these fields. So it sees 9 different values that I can work from. So that's straightforward. You dump the files out as a CSV or a TSV in Excel. and then you read them in here. Now, necessarily, if you're working with tab-separated values, don't use the CSV function. Use the TSV function. Or you could use read table and pass it the parameter that the delimiter is a tab symbol. You could do stuff like that. But this function is one of the easiest things to work with when you're trying to read in data. Are you required to have a header if you pass a file in this way? No. But if you don't have a header, it's probably better for you to say header equals false as a parameter to read CSV. Then it will not assume it's there. Okay, so we've now read these data in. I had a couple things. One of my very, very favorite functions within R is the summary function. So when I typed provinces all by itself, it just spat out what the table looked like. I can do a summary on that instead. And now we see that measures of spread are computed for us auto-magically. So we had 9 values that we input. It immediately reports that the minimum value was 104. I need to improve my numerical literacy here. 1,145,861. Did somebody say Zuma's name? I don't think so. You did not. 114, 15. No.